Good afternoon. So as Hayes already mentioned, I will present to you some of the recent work that we did, partially financed by SECR. Thank you. And this is work that was carried out in collaboration with Dr. Gift Zantane from Alacars, a company here in Switzerland, as well as Simone Zaffatoni and Maurizio Barbato from Subsi. And the work that I'm showing here, partially financed by SECR, but most of it was financed through an SNF NRP 70 project. And it was actually two PhD students, Viola and Lucas, that did the lion's share of the work that I'm going to show to you this afternoon. So I want to start out by briefly explaining why we are interested in Alacars in the first place. And I would like to show to you actually two reasons. So the first one is if you look at the cost aspect. So what is shown here from a publication listed here at the bottom from 2015, a chart showing the power-specific capital cost plotted as a function of the energy-specific capital cost. And you can then identify, for example, two regions. The first one right here that includes pumped hydro storage, advanced adiabatic compressed energy storage, and the simpler diabatic form of compressed energy storage. And a second region that includes some of the well-known battery storage technologies. So you can see that as far as the energy-specific capital cost is concerned, these compressed air energy storage technologies are roughly an order of magnitude lower. There is also a study that was actually carried out as part of the SECR project by a group including people from Hochschule Luzern, PSI, and University of Geneva. And they compared pumped hydro, compressed air, and power to methane back to power, as well as batteries for short, medium, and long timescale storage applications. And here also they found that at least for medium timescale storage durations, the levelized cost of electricity storage is lower for compressed air than, for example, for batteries and power to methane back to power, and comparable or perhaps a little bit lower than pumped hydro. Then moving on to life cycle analysis. From the same publication I mentioned on the previous slide, they looked at life cycle greenhouse gas emissions. And here again, if you look at the medium term storage timescale, you find that advanced adiabatic compressed energy storage is comparable to pumped hydro, which in general is regarded as a very environmentally friendly storage technology, if you disregard the fact that you need to flood mountain valleys. Okay, and then finally, also from a recent publication, they studied various storage technologies in terms of the energy that you need to expend to actually construct the storage itself over, the energy that you store over the entire life cycle of the storage technology versus the amount of energy that you actually need to invest to construct the storage in the first place. So for compressed air, pumped hydro, and again, various battery technologies. So energy storage over energy invested, and you can see here that compressed air and pumped hydro are orders of magnitude more attractive in this metric than battery storage technologies. And compressed air actually turns out to be a little bit more attractive than pumped hydro. So having said that, these are a couple of the reasons why we believe that compressed air storage actually merits a closer look. And this closer look is required because in its adiabatic form, it hasn't actually been studied yet in any detail. Okay? So to set the stage, what I'm showing here is the close similarity between pumped hydro and compressed air storage. So you're all familiar with the basic idea for pumped hydro. You have, for example, excess electricity, use it to drive a motor. The motor drives a pump. that pumps water from a lower reservoir into an upper reservoir. And then you have a compressor, which is actually the compressor that actually turns out to be a little bit more attractive than pumped hydro. So having said that, these are a couple of the reasons why we believe that compressed air storage actually merits a closer look. And this closer look is required because in its adiabatic form, it hasn't actually been studied yet in any detail. Okay? So to set the stage, what I'm showing here is the close similarity between pumped hydro and compressed air storage. So you all familiar with the basic idea for pumped hydro. You have, for example, excess electricity, use it to drive a motor. The motor drives a pump. That pumps water from a lower reservoir into an upper reservoir. In the case of compressed air storage, the principle is exactly the same. You use excess electricity, you again drive the motor, but the motor now drives the compressor that takes in ambient air. It's compressed to temperatures of, let's say, about 600 degrees, which by itself you cannot store because it's too hot, for example, for both salt or rock. So we cool it down in a thermal energy storage to temperatures of roughly 30 degrees, and then the cooled air is actually stored in the cabin. So if you actually need to retrieve energy, you simply reverse the process. In the case of pumped hydro, you let the water drive a turbine that drives a generator that provides electricity back to the grid. In the case of compressed air, you let the cool air flow out of the cavern through the storage, where it gets heated up. The heated air then drives the turbine, which drives the generator, which provides electricity back to the grid. So the principle is very similar. One of the advantages beyond the ones that I mentioned on the previous couple of slides, of course, is that we don't need to flood any mountain valleys. And at least in principle, it would be possible to build the entire plant on the ground. Okay? And in the context of the collaboration with Alakais, we are particularly interested in, for example, reusing existing tunnels or also military caverns as a storage possibility. And before I move on, I want to mention that, for example, for pumped hydro, the real-life cycle efficiencies are usually quoted to be about 80 to 85%. And theoretical studies show that for advanced adiabatic compressed energy storage, efficiency should lie 65, 70 to about 75%. And this is actually one of the reasons why these pilot scale experiments were not just of interest to us, but actually also of great importance. So far, as far as we are aware, there are no other pilot scale compressed energy storage plants anywhere in the world. So in this pilot scale plant, there are, as far as we know, 3 world firsts. The first one is that it's actually the first pilot scale plant to begin with. And here I want to mention very clearly that we were mainly interested in actually demonstrating the compression part of the process. So we did not include the turbine because this simply would have driven up the cost of the entire infrastructure and experiments. Then, as far as we know, it is the first pilot scale plant in which we actually use a hard rock cavern. And to keep the costs low, we were interested in investigating how well this cavern will work if we do not line it with some, for example, plastic sheathing to try to make it airtight. And then these were also the first experiments where at a pilot scale we had a combined sensible latent heat and thermal storage. So the sensible storage had a capacity of about 12 megawatt hours and the latent storage about 170 kilowatt hours. And this plant was built in a decommissioned tunnel. Okay, so this is a map on the left of the south of Switzerland, in particular the area around near Biasca. So this is a small city north of Bellinzona. And the tunnel is shown here in red. It's about 3 kilometers long. And here you see the northeastern portal. And if you're wondering why would somebody build a tunnel for 3 kilometers around or in a mountain where you could just as well drive around it, the reason is that the Gotthard base tunnel, the southern entrance is around about here. And during its construction, they were actually trying to find a cheap way to take the excavated material and deposit it right here, where it says deposit. And this is now a pretty decent sized hill, which is here still unfinished, that has part of the material that was excavated from the Gotthard base tunnel. So if you go into the tunnel, it looks like this for about 800 meters. So after about 800 meters, we actually built this research infrastructure. And it's shown schematically here, using 2 concrete plugs and steel doors that I'll show in a second. A cavern of about 120 meters length was built. The tunnel has a diameter of about 5 meters. And inside this cavern, we locate both the sensible heat storage that I mentioned before, as well as the latent heat storage. It is then supplied with compressed and heated air by a compressor that then typically flows through the latent storage, then back to the, then through the sensible storage, and then the cooled air goes into the cavern. Now, one thing that I did not point out so far, which is another unique feature of this pilot scale plant, is that the thermal storage unit is actually located inside the cavern. Okay, so there are other plant concepts in which the thermal storage units are located outside the cavern, which means that the storage structure itself needs to bear the pressure that comes out of the compressor, which makes the whole storage a lot more complicated to build because it needs to support that pressure difference. And if you build it inside the cavern, it basically doesn't experience really any pressure difference worth speaking of, which simplifies the construction and then of course also the cost. So this is on the right hand side a picture of one of the steel doors with the part of the concrete block, and then here on the left hand side you see a picture of the sensible heat storage. It's a little bit less than about 3 meters tall and roughly 10 meters long, and it is filled with ordinary rocks that you can excavate in Switzerland from a riverbed. Okay, and if this seems a little bit simplistic, then I can assure you that this actually works extremely well. And these rocks are attractive to us because they are basically free, extremely cheap, and their thermal properties are actually very attractive. And we have also shown through previous experiments as well as dedicated studies that these rocks withstand cycles of up to about 570 degrees or so without any problems. Then the latent storage is roughly a cube of about 0.75 meters in each dimension. And we used a eutectic aluminum copper silicon alloy as the phase change material and encapsulated it in steel tubes that you can see here. And this alloy has a melting temperature of about 520 degrees Celsius. Okay, so I'm going to show you a couple of plots with results from the pilot scale plant. So the first one is a plot of the temperature of the air in the cavern and the temperature of the rock. So these are both measured. So the temperature of the rock is measured about 20 centimeters into the actual rock. And so I'm showing these temperatures as a function of time. Now, what is shown with a light blue background is what we call a pre-charging phase. And we carry out this pre-charging phase to simulate essentially the quasi-steady operation to which such a plant would be subjected. And this is simply a way for us to reach a representative, realistic state more quickly. And then in white and gray are usually shown then the charging and the corresponding discharging phases. So, as I mentioned, in red we have the experimentally measured cavern temperature, and you can see that during the pre-charging phase this rises relatively slowly, and then as you go to the first discharging phase you see a very steep drop, and then again a steep rise as you go through charging, and this continues. And a similar pattern can be seen in the rock temperature, except that it lags behind the cavern temperature, which would be expected, of course. And then in black, as a full line and as a dashed line, are the results of two simulations with different heat transfer coefficients between the rock, or between the air and the rock. We carried out this sensitivity study because we don't know the precise value. And we find that there is, of course, a difference, but it's not extremely sensitive to the precise value. And you can see here that, for example, the difference between 5 and 10 watts per square meter Kelvin is roughly half a degree for most of the duration. And the agreement between the experiments and the simulations is pretty good, even during the steep transients that you get when you switch from charging to discharging and vice versa. Then some temperature profiles from the latent storage. So what is shown here is the temperature on the x-axis as a function of the axial or the vertical position in the storage. The symbols denote, the circles are measured air temperatures, and the triangles are measured temperatures of the actual phase change material. And the black line and the dashed line are the simulated phase change material and air temperatures. And we show these temperatures for various times, so at the beginning, and then after 10 hours, 18, 27, and 70 hours. And you can see, as would be expected, that there is actually little thermal stratification in the latent storage, and that the agreement between the simulations and the experiments is pretty good. The biggest discrepancies arise during the time when the phase change material actually goes through the melting process. And the melting range of the phase change material is actually shown with this shaded region right here, but even there, the stratification in the storage is actually very small. And this is in contrast to the temperature profiles that we expect to see in the sensible storage. So here again, temperature on the x-axis and the vertical position on the y-axis, again for the various times that I mentioned before. So here we see the typical stratification in the sensible storage, which is why it is also called a thermocline storage. And overall, we observe again that at the various times, the agreement between the simulations for both the air and the rock temperatures and the experiments is very good. Now, a more detailed look now at the latent storage. So this is now the temperature in one of the layers with the tubes encapsulating the phase material that is almost at the bottom of the storage as a function of time during 4 charging and discharging cycles. So here again, white background is a charging phase and the light gray background is a discharging phase. And this light red background again denotes the range in which the phase change material changes phase. And we have now in red the measured air temperatures, and then in with the dashed line the simulated air temperatures, and then with the full black line the simulated temperatures of the phase change material. And you can see that with the exception of the first charging and discharging phases where there's some discrepancies, then later on the agreement between the simulations and the experiments is actually very good. So this gives us confidence that the model that we have developed can be used not simply to study plants of a pilot scale size, but also in potential industrial scale plants. So why are we interested in having both the sensible and the latent tests in the first place? And this is a very reasonable question to ask, and in very simple terms, the reason can actually be traced back to this plot. So during discharging, we operate the storage such that we supply cold air from the bottom and the hot air flows out of the top. Which means that during discharging, these entire profiles are simply moving up, which means because of the spatial gradient in the profile, that the outflow temperature, the temperature up here, would actually drop during discharging. And it is that drop in the outflow temperature that then gets passed on to the turbine. So a lower inflow temperature would lower the efficiency of the turbine, which would then lower the efficiency of the plant. And this is not a problem if we then have the air that flows out of the sensible storage flow through the latent storage before it goes to the turbine. Because in the latent storage we actually have spatially invariant temperature profiles. So if we now compare the inflow temperature to the latent storage, which is similar to the outflow temperature of the sensible storage, with the outflow temperature of the latent storage, which would be similar to the inflow temperature of the turbine, you can see that there is an increase in temperature and a shallower decrease with time that would then help us have the turbine run more efficiently and therefore also the entire plant. So this is one of the reasons why we're interested in actually combining the sensible and the latent storage. So, at the beginning I mentioned the efficiencies of such compressed air energy storage plants. And I mentioned that so far there have only been theoretical estimations that usually lie 70–75%. So one of the main things that we wanted to find out is what do we actually see in the pilot scale plant. So what I'm showing in the table are from 2 of the runs that we carried out with the sensible storage. And each of these runs consisted of slightly different charging and discharging cycles. So our interest is mostly in run 2, because there the charging and discharging cycles were exactly the same. And then I'm showing the efficiency of the thermal energy storage, which at the moment I'm not particularly interested in. And I actually want to focus on this column of data right here. So you can see that the efficiencies range from about 65% up to about 70%. Okay? Which we were very pleased by, because we didn't really know what to expect in a much smaller scale plant that is typically analyzed in theory. And for transparency, I need to mention that, as I mentioned at the beginning of my presentation, this pilot scale plant did not include a turbine for cost reasons. So what we're doing here is we're using the actually measured data where we can, and then we estimate the performance of the turbine with an isotropic efficiency of 0.85, and motors and generators were taken to have efficiency of about 0.97. Okay. So what we've done is we basically demonstrated at the pilot scale that this combined storage really has a benefit. And then with the pilot scale plant, we demonstrated the advanced compressed air energy storage concept with a mostly unlined cavern to keep costs low at a potential industrial scale. We tested both storages with temperatures of up to about 560 degrees Celsius. The tests, well, actually both tests were located inside the cavern to simplify their construction. And the estimated plant efficiency of about 65, 70, 75% based on experimental data. And based on these investigations, we are now shifting our focus in SCCR phase 2 from mostly technical to now more also the economic area. So we are interested in answering the question, where in Switzerland could we build such plants? And what capacity and power ratings would these plants need to have when in the future they're connected to the electricity grid and they need to react to the corresponding excess or maybe lack of electrical energy? Okay, so I mentioned at the beginning that I'm only showing part of the results from this SNF project, and there are a variety of other partners, including some here. So we have partners here at EPFL, Sophia Hauser and Selma Bilder. This is Gift Sampany from Alakais. Then 3 colleagues from PSI that do the sustainability and economic analysis, and Maurizio and Jonathan from SUSE. So as I mentioned, this was financed, most of it through an NRP 70 project and SCCR, and Alakais was also assisted by a grant from the Swiss Federal Office of Energy when building the pilot plant. And if you're interested in watching a YouTube movie produced by SNF about the project, this is a QR code for it. And I'm at the end of my presentation. Thank you.